My name's Evan Olson, and I'll be solving problem 7.10 of the Fundamentals of Heat and Mass Transfer 8th edition. So for our problem statement, we have a flat plate subject to parallel flow on both the top and bottom surfaces, characterized by a free stream velocity of 5 meters per second and a bulk temperature of 20 degrees Celsius. We need to determine the average convection heat transfer coefficient, the heat transfer rate, and the drag force for a plate that is 2 meters long, 3 meters wide, um, for flat airflow, for two surface temperatures on the top and bottom of 30 degrees Celsius and 80 degrees Celsius. So for our schematic here, not to scale, we have our flow going on both sides of the plate, and we have our two different surface temperatures, which I will treat independently. To first solve for our average convection heat transfer coefficient, we need to determine whether it's turbulent or laminar flow. And so we first need to find our Reynolds number of the flow. And that equation is the just standard Reynolds number equation, which is equal to the density times the free stream velocity times your position along the plate divided by your dynamic viscosity. Um, And the properties of the air should be taken at the film temperature, which is the average temperature between the bulk air temperature and your plate surface temperature. And at that temperature, the properties of the air are given here. A density of 1.1614 kilograms per cubic meter and a viscosity of 184.6 times 10 to the minus 7 Newton seconds per square meter. And for any given x, the Reynolds number will turn out to be 3.146 times 10 to the fifth times x. And so our critical Reynolds number for a flat plate is given to be 10 or 5 times 10 to the fifth. And so any value above that is going to be turbulent, and any value below that's going to be laminar flow. And there's some transition region in there, but we're assuming that it's going to be tripped um, instantaneously between laminar and turbulent flow to avoid any additional complexity. Uh, and so we can calculate where the transition between laminar and turbulent flow is going to occur along our 2 meter plate. And that turns out to be at 1.589 meters. So that's around 75% of the plate length. So you could potentially just assume that it's all going to be laminar flow and get an estimated solution. But I went for just assuming it's a mixed boundary layer between laminar and turbulent flow. So you would evaluate your convection coefficient at every single point, whether it's laminar or turbulent. In my case, using MATLAB. And so we can set up our conditions here for our Nusselt number correlation. If it's turbulent flow, our Nusselt number correlation is given here, 0.0296 times our Reynolds number at that location to the 4/5 power times our Prandtl number to the 1/3 power. And if it's laminar flow, very similar, except the equation is 0.332 times our Reynolds number to the 1/2 and our Prandtl number to the 1/3. So if we evaluate our Nusselt number correlation and then plug in for h of x, and then to get our average heat transfer coefficient, which is what the problem asks for, we can take the integral over h of x dx between our whole plate length and divide that by the length to just get our average. And for our two surface temperature conditions, we get values very close to each other um, of 5.987 watts per meter squared Kelvin at 30 degrees Celsius surface temperature and 5.9733 watts per meter squared Kelvin at 80 degrees surface temperature. And to get our average heat rate caused by the convection, it's just HA delta T, and that gives us uh, negative 359.2 watts and negative 2150.4 watts for both our surface temperature conditions. And that's negative as in heat is flowing from the plate to the air, since the plate is at a higher temperature than the airflow. To find our drag force, there are similar friction coefficient correlations for different Reynolds numbers. And so I did the same method where I calculated the friction coefficient at many different points of x, and then I integrated them together using these correlations. uh, to get our average friction coefficient. And then now that we have the friction coefficient in our code, we can evaluate the drag force caused by the flow, the average drag force over the entire plate, which is just 1/2 times our average friction coefficient times rho times our free stream velocity squared times our surface area. And that evaluates out to be around 0.2831, with the units being newtons, at 30 degrees Celsius and 0.2812 at 80 degrees Celsius. And for the second part of this problem, it asks us to find the same answers, the convection heat transfer coefficient, heat transfer rate, and drag force. But for this time, it's a zero point 0.1 meter long and 0.1 meter wide plate, uh, with in water flow instead of airflow with the same surface temperatures. And so we can follow the exact same process for this problem, except we're going to use different uh, fluid properties for water, except for air this time. And same here, we're evaluating at the film temperature between the plate surface and the fluid. And our Reynolds number equation will evaluate out to be 5.8655 times 10 to the 6 times x. And for the same turbulent and laminar critical number, we get our transition to turbulent flow at 0.085 meters. Now, in this case, the plate length is zero point 0.1 meters, so this is 85% of the plate length. So again, you can make that assumption that most of the flow is laminar, um, but just for more precision, I just assumed it was a mixed boundary layer and evaluated at every point in X using MATLAB, using the same exact Nusselt number correlations, which resulted out in uh, average heat transfer coefficients of 1204.2 watts per meter squared Kelvin at a 30 degrees Celsius surface temperature, and 1359.7 at 80 degrees Celsius. And this is much higher than that of the airflow, of course, since fluids typically have much higher convection coefficients due to their density. And so we can also evaluate out our heat rate due to convection for the water, and it turns out to be around 7.22 times 10 to the 4 watts for 30 degrees Celsius, and 4.894 times 10 to the 5th watts for 80 degrees Celsius. And our drag force here is going to be much higher because it's a much more viscous fluid and dense fluid flowing over our surface. We can use the same exact correlations for our friction coefficient, and we get values for the water flow of 57.8 newtons at 30 degrees Celsius and 45.4 newtons at 80 degrees Celsius.